see. Final review. This one. Okay. Hello. Okay. Yeah. And as you all know, this Friday will be finals, and today we'll have a final review around chapter 9 and chapter 10. Okay? And yeah, just like the previous reviews, this review will be mostly just go over the concepts in chapter 9 and chapter 10. Okay, so let's start with chapter 9. Chapter 9 talks about Laplace transform, and this is the Laplace transform. Or at least that's the one we talk most about. It's a bilateral form of Laplace transform. And it's a generalization of Fourier transform where in Fourier transform we have e to the minus j omega t here, but now this j omega we consider generalization here. The j omega become an arbitrary complex number s here. So big X of S is defined as integration minus infinity plus infinity x of t e to the minus st dt. We are integrating over t, and s is some complex value. It can be any complex value, but as we'll see, it will converge on only some of s. It's called the ROC. But yeah, so we like to analyze s in terms of its real part and the imaginary part, sigma plus j omega. And we think about Fourier transform is when sigma equal to 0. So you are only integrating e to the minus j omega t. And here we have a slightly more generalization of that. So we do this derivation, and we see that the x of s equal to Fourier transform of x of t times e to the minus sigma of t. So if sigma equals 0, then it's, your x of j omega is just the Fourier transform of x of t. And as we say, x of s don't converge sometimes, and what we really mean is that there is a concept of ROC here. So in Fourier transform, we just say either the Fourier transform converge everywhere or it doesn't converge everywhere. But for the Laplace transform, there is this concept of ROC. So this transformation, this formula will converge on some value of s, and it doesn't converge on some value of s. And we draw those those shaded areas. And the ROC is actually an important part of the Fourier Laplace transform. So sometimes you will get some algebraic expression, but if you are just picking different ROC, you are actually corresponding to the Laplace transform of two different signals in the time domain. So here are the two examples that we like most about in chapter 9. So in example 9.1, we have this e to the minus atu of t, so it's a right-sided function, and the Laplace transform into 1 over s plus a, and with the ROC being where the real part of your s needs to be bigger than minus a. And then we have a very different function in the time domain is e to the minus atu of minus t. So it's a left-sided signal. And we see that it Laplace transform to the same expression in s domain, so 1 over s plus a, but the ROC is on the minus a side. So this is example 9.1 and 9.2. And because they have this nice 1 over sa fraction, we also use them to do all sorts of the inverse Laplace transform. Okay. And yeah, so skip ahead a little bit. So we also use those two things to do a lot of the inverse Laplace transform. So we'll do partial fraction expansion. So if mostly for rational functions. So for rational function, we'll try to do partial fraction expansion to break your big X of s into terms like the summation of 1 over s plus different a, and then you look at ROC to decide whether your RC looks like is the right side or left side. Then you reverse back into this e to the minus atu of t or minus e to the minus atu of minus t. Okay, so that's the inverse Laplace transform. But for now, let's look at those properties of ROC. So first property says that ROC should consist of strips parallel to j omega axis. And this is from that from we say the Fourier transform either converge or doesn't converge. So each straight line in the S domain corresponds to Fourier transform for different sigma, from what we say here. And if that Fourier transform converge, then we say that whole line is in RC, etc. So the RC are strips, and then for rational function, obviously RC doesn't contain poles because the poles are just infinity. And then we have those four property. We say that if X is finite duration, then RC should be everywhere. Because finite duration, you can analyze it, and you found out that the integration always converge. And then if it's right-sided, if X of t is right-sided, then your RC is kind of also like right-sided. So example like this, you will extend to the right infinity. And if your signal is left-sided, your RC will extend to left infinity. And if you are two-sided, then your RC will be one stripped. Okay, so just one stripped. So yeah, so your RC can be, but this one strip can also extend to everywhere. This is a little vague, but anyway, the important thing here is that there is only one strip. You cannot have two separate strips here, just from the left and the right analysis. And then maybe I should enhance this. Yeah. And also, if you are rational, then your rational function you can decompose your numerator and denominator. So numerator and denominator are both polynomial, and you can calculate the roots of those polynomials. Those will be the poles and the zeros of your big X of S. And the more important things are the poles, which are the roots of the denominator. And anyway, then your RC will be bounded by those poles. And yeah, and just like we said before, poles should not be RC. So once again, see here in this picture, you see there are two poles here. So your RC will be bounded by the poles, so it can either be this section or in the middle section or left section. So there are three choices, just by looking at the poles of the poles on the S plane. And yeah, and finally, is still the same example, but can still be explained by the same example. And we say that if you are rational and the things are bounded by poles, then just combine this left and right analysis, you see that if your signal is right-sided, then your RC should extend from the rightmost pole and extend to right infinity. And if you are left-sided, you should extend from leftmost pole and extend to left infinity. And if you are two-sided, then you are sun-stripped in the middle. Okay. So those are the RC of Laplace transform. Question? Stop a little bit? No. Yeah, then we talk about inverse Laplace transform. So there are two ways to inverse Laplace transform, and the first one is most general, where we say that you can do a contour integral inside your RC from minus infinity omega to plus infinity omega. Okay, so this is contour integral 1 over 2 pi j, and the integration through this contour and the big X of S times e to the st ds. Unfortunately, this is very general, but we don't know how to do a contour integral. So when you take more math class and learn how to do complex analysis, you will be able to do this. And what we actually do is this kind of cheating way of doing partial fraction expansion. And as we say, we like to use our favorite example 9.1 and 9.2, and they tell us how to do inversion of this 1 over s plus a. So we have a rational function, then you decompose your denominator into these factors of roots, and then you can write them into partial fractions. And partial fractions we have done a lot of time. I think it's things when we are talking about Fourier transform. So let's skip that. Here is, so you write this as a over s plus 1, b over s plus 2. So some coefficient over fractions, and you can solve for those coefficients in various ways. You can either multiply all everything and try to solve the linear equation, or here you have something more smarter where you multiply with the root terms and something will be 0, then you can read from here, etc., etc. Okay. Anyway, you can do partial fraction expansion, and then you can look at the RC and you invert it. And yeah. And here is something extra. We say that the partial fraction expansion can only be done when the upper side has less degree than the lower side. So if you have equal or more degree on the upper side, then you do a division, so you get some extra quotient terms. So those extra polynomial here, B, P, oh, it should be Q here, right? Didn't notice. Okay, so it should be Q, BQSQ. Okay, BQSQ, BQS2Q, and plus some B0. But anyway, so these polynomial terms, you can also look at the formula to invert that. They are a little divergent. So this constant term will inverse the Laplace transform into delta function, and those SQ to the Q terms will inverse the Laplace transform to those U sub n function, which are singularity functions. They are more singular than the delta function. You can just look at table and write them down. Okay. So that's inverse Laplace transform partial fraction expansion. And then the properties, we just list the table. Here, the first thing to remember is there is a RC issue. Okay. So unlike Fourier transform, in Laplace transform there is RC, and when you do any of the property here, you need to think about how the RC change. And RC that usually has this form, so just look at the linearity. So a small x plus b small, so a small x1 plus b small x2 Laplace transform to a big x1 plus b small big x2, and but the RC is now it usually has this form, so it has the intersection between R1 and R2. So you want big x1 to converge and big x2 to converge, but there is also a list. Okay. So this we have a list here because when we do this transform, you can cancel some poles here. And say your rational function, then you want your RC to be bounded by poles. So this intersection can get extended when the boundary poles get cancelled out, then you extend to the next pole. Okay. And yeah, so you see many of the things have the same thing here. So it is at least here and it is at least here. And anyway, so let's just walk through them really quickly. So obviously we have linearity, and okay, so this is really small. Let's see here. Okay, better. Yeah, yeah. So that's the linearity. Then we have time shifting. Is just like Fourier transform. So you time shift in time domain, you get this e to the minus st, and the s shift is also similar. So you shift s by this s0, then you get the e to the s0t in the time domain. And this will also shift the RC. And then you do time scaling, and you get so time scale t to at, then s will scale by 1 over a, and also will divide by this a absolute value. So this is all similar. So you like stretching time, then you squeeze in s, etc. And this will also scale your RC with the factor of a. And then we have conjugation. S got complex conjugation. Then big X also get complex conjugation. Also S also get complex conjugation. So you have 2 star here. And then the convolution equation as usual. You have convolution in time domain. You have this multiplication in the S domain. Excuse me. And but we don't quite have the other side around because we don't do convolution in S domain. But anyway, then we have differentiation in time, and we get the HRS vector in the S domain, and differentiation in S, you get this minus t vector. So those are still like Fourier transform. Then integration is a little it deviates from the Fourier transform a little bit. So your integration in the time domain, you get 1 over s from x domain, from the S domain. But in the Fourier transform, you have the weird delta function, but here you just don't have. So the differentiation and the integration in time, just they are perfectly inverse of each other. But there is something weird in the RC you need to keep track of. So yeah, so for example, here the RC change because you are multiplying this 1 over s and this 1 over s has its own RC being real s of bigger than 0. Because you are thinking about you are basically doing a convolution with the unit state function. Okay, and then we have those two HR theorem that didn't happen in didn't have in the Fourier transform. So initial and final value theorem, they have this a little weird condition that you want your x to be basically causal, so x of t equal to 0 for t less than 0. And then you want the x to be not too bad at t equals 0, then you can calculate x of 0 plus by doing this weird limit of s times big X of s taking s to infinity. And also you can find the final value of x of t. So x of t as t goes to infinity, as s goes to infinity, s times big X. S goes to 0 of s times big X of s. So they are just here, they are, well, we don't find too much critical application of them, but it's nice to use them to check the correctness of your calculation, and also there can be problem that ask you to use them to do some detective work around your Laplace transform. Okay. Yeah. So they are interesting, and how do I? Okay. And then next one, we have our, okay, so it's still small. Wait, when I go up, oh, okay. So when I go up, you cannot see the, that's annoying. When I go up, you cannot see the pointer. Okay, but I think we should still do this. It's better. Yeah, so we have also this table of Laplace transform. So I guess the two most important one is the 6 and 7 we talked about. So they correspond to this 1 over s plus a. And here some of the things can be just, so this is u and u of t and u of minus t are just a special case of a equals 0, or it's actually alpha. So alpha equals 0, you get u of t and u of minus t. And then you can also derive from here the higher order terms. So you can derive those 1 over s plus a to n by doing like differentiation with s here. And then you do the calculation carefully, you get this 8 and 9. So let's go bigger. So if you have nth power here, then you get this t over minus 1 over minus 1 polynomial. So basically you get the powers of t here. So here the partial fraction expansion is very complete. So if you have higher power, then higher order roots in your partial fraction expansion and in your rational function, then you can partial fraction expansion into these higher power terms, and you can still do Laplace transform. You can still look at RC and do inverse Laplace transform back to either this or this. Okay. And then the other thing, we have other thing. Then yeah, we have other things that's useful. You can look at those sine and cosine. And also, as we said, this s to the n equal to those singularity function u sub n. And and also your signal is delta function, then you get e to the minus s times t, this big T. Okay, so if you are big T equal to 0, then it's just 1. Okay, so that's Laplace transform pairs. Okay. Oh, a little slow on time. Okay, so let's go a little faster. Then stability. Okay, so your TI system is stable if only if the RC include the j omega axis. So as we said, the derivation is a little ambiguous. Not ambiguous, I guess. A little, I guess, not rigorous enough. But anyway, this is what we believe. So LTI system is stable if only if the RLC contains the geometric axis. Then causality is we actually don't get if and only if here. So we say if the system is causal, then the RLC is the rightmost RLC basically. So the RLC include the right half plane. That's just because the causal system is right-sided, but the converse is not true, because you can easily construct something that's right-sided but not causal, and the RLC is still right half plane. But if the system is rational, then it works. If the system is rational, then you are causal if only if the RLC is the rightmost one. And we can also, so we didn't have it here, but you can also combine these two and think about if you have a rational system and you want it to be causal and stable, then you find out all the poles need to be on the right hand side, because you want the rightmost RLC to also contain the geometric axis. Okay, so that's causal and stable, and then we have using Laplace transform to solve our linear constant coefficient differential equation. So for bilateral Laplace transform is very similar to Fourier transform. So if you do Laplace transform on both sides, then you can write down this h of s, and it is polynomial of x over polynomial of x with coefficient b. Those b are the coefficient of x, and the coefficient a from coefficient of y. Okay, and so you can always write it down, but to solve this, you will need to supply other conditions. So you can, because as we know, this is a Laplace transform, and then you need to substitute the RLC. And then you can either say you are stable, then your RLC need to contain the real line, or you are causal, then you need to pick a rightmost RLC, etc., etc. It will depend on the problem given to you. You need to do the detective work. And then we spend quite a bit of time talking about these extra things. So we actually have another kind of Laplace transform, which is, we call it a unilateral Laplace transform. And it can be used to solve the also differential equation, but but with initial or boundary values. So remember, before we usually solve the differential equation with the initial race condition, which correspond to the system being causal and LTI. But you can also have your differential equation given with some initial value. So you just say like y of 0 equal to something, and y prime of 0 equal to something. And when we solve differential equation like that, so one thing to notice that is the system is not LTI anymore, because you are bounded by the initial value. And but that's also very useful in a lot of application. In engineering, you want to solve that, and to solve that, you use this unilateral Laplace transform, which is defined very similar to Laplace transform, but the integration starts from 0 minus. 0 minus meaning that when you do integration, you also include the singularity at 0. Okay, and and because you are integrating from the 0 minus, so your RLC is always the rightmost one. And for this thing, you don't need to specify RLC, so you only do the rightmost one. And they also have properties you can check here. So like for time scale, and so everything revolves around this integration from 0 minus. It's also because of this integration from 0 minus, you can solve initial value problem basically. And yeah, so for example, we must have a bigger than 0 here. And then the differential property is very useful here. So you have dx dt, and you see that they actually depend on the value of x on this boundary of 0 minus. And the initial and final value theorem now is more natural, because we basically don't care about the x of t for x less than 0. So we can kind of assume the x of t is just less than 0, equal to 0 for t less than 0. Okay, so we also have initial value and the final value theorem that looks more natural. And as we said, the differential property is very useful, and so it can be derived from this integration by part. and then you can do this multiple times and get the higher order different derivative. So for example, the second order derivative will become this thing. So maybe we should say once again, say it once. So d dx dt unilateral Laplace transform to s times big X of s minus x of 0 minus. And then if you do the second order, then you get this s squared big X of s and then minus x of 0 minus x prime of 0 minus, where x prime is the dx dt. Okay? And we had some example that give you some intuition about this x of 0 minus. Is extend around 0. And anyway, then from this we see how to solve the initial value problem. So we are given a differential equation like this. So initial value problem is like that. You have a differential equation and you have two initial value. And the initial value here, because we are using this from 0 minus, so we put the initial value around 0 minus. But you should see from homework that you can also shift this 0 minus around. But anyway, so here we center around 0 minus. So y of 0 minus is equal to something, y prime of 0 minus is equal to something. And then we use unilateral Laplace transform on everything. And so each derivative, excuse me, and just me. Here we didn't write x of t. So what x of t is in the lecture. But anyway, so we do unilateral Laplace transform on everything. So this y becomes script y, and so this dy dt from this differential property. So you get s times script y, but you also get this minus y0 term. Okay. And then the square y dt, then you get this a squared as the Laplace transform, a squared of big Y as the Laplace transform will have, but you also get this beta and gamma term here. And then you can write down big Y, what it is, and is this thing, then yeah. And then you can do the inverse unilateral Laplace transform to solve all your initial value problem. Okay. Okay, so that's chapter 9 and question for now. Okay, yeah, so I guess say a little more. So you want to solve this, then once again you will do partial fraction expansion. And do we have? I forgot to list that. Yeah. We should also okay. So table 9.3 and there should be a 9.5, 9.4 for the table for unilateral Laplace transform, and yeah, so those will also be included. Okay, yeah, so that's the unilateral Laplace transform, and okay, then we go to chapter 10. Which is the Z transform, and it's very similar to the Laplace transform. It's a discrete version of the Laplace transform basically, but it's a little weird because we are, instead of those e to the st, e to the minus st, we are just using z to the n. Okay. This is because so the geometry is very different. This is because we want to include the period in omega. So omega has a 2 pi period when your time is discrete, and we do that by just writing z here. And anyway, this is the definition of z transform. Big X of z is summation n from minus infinity to plus infinity, x of n z to the minus n. And just like the Laplace transform, we can separate z into polar coordinates. So z equal to r times e to the j omega. And we find out that so this omega is just like the omega in the discrete line Fourier transform, and omega will from 0 to 2 pi. And this r is like scaling your Fourier transform. Find out that if you pick z equal to r times e to the j omega, then that's just your fix on r, then it's just a Fourier transform to the different signal. So the signal of x over n times r to the minus n. Okay, and we can compare to z transform. Compare z transform to a Laplace transform a little bit. So you see the Laplace transform has those ROC with straight strips, and the z transform has those ROC are basically rings. So everything are divided by circles. And in Laplace transform, you have these geometric axes that's spatial. They correspond to the Fourier transform. And in Z transform, you have this unit circle that correspond to the Fourier transform. And you also have poles and the zeros on the plane. And as you will see soon, in Z transform, the 0 and the infinity are kind of spatial. And you want to specify whether your RC includes the 0 or infinity. And here are some comparisons. And just like the Laplace transform, Z transform, we have those two spatial functions. So the right-sided exponential x of n equal to a to the n u of n. And we do Z transform, and we found out that the Z transform to 1 over 1 minus a z minus 1, with the RC being z bigger than a, so outside of this a pole. And you see that this is more ugly than Laplace transform. The first is for Laplace transform, where you will have just 1 over s plus a. And this also makes, so because this is a more ugly form, so the inverse transform of Z transform is also harder because we want to fit into this form. Okay. And anyway, get back to our example. So this example, then we also have example 10.2, similar to example 9.2. So now we have this left-sided exponential, and we found out that it has a same algebraic expression in this big X of z, but the RC is inside this pole. Okay. And yeah, so RC is this circle filled up inside. Okay. And yeah, and then we go to the properties of these RCs of this transform. So as we say, the RC are rings, and rings should be correspond to those R where your Fourier transform converge. And then RC doesn't contain poles as usual because poles diverge. And then then we have those finite duration analysis. So finite duration, your RC is everything. But now, as we say, the 0 and the infinity are a little weird. So your RC is everything except 0 and the infinity might not in your RC. And where 0 or infinity is in your RC, you need to look at the n1 and n2 and think about, so say, if you have positive z terms, then obviously z to the infinity. So I guess the negative n term means z to the positive power, then z to the infinity will not converge. And then you have z to the negative power, then z equals 0 will not converge, etc. So we need to look at n1 and n2 and to see where 0 and infinity is in your RC. And then similarly, property 4, we say the right-sided sequence, then similar to Laplace transform. So Laplace transform say right-sided sequence, your RC is right-sided. And here we say Z transform, we say the sequence is right-sided. Then the RC is the outer ring, so like outside of some ring. And but similar to this, is everything outside but the z equals to infinity might not be included. You also need to look at your right-sided boundary. You need to look at the cutoff to see whether the infinity is included. And also left-sided signal then is inside of something, but 0 might not be included. This part you need to check. And finally, if you are two-sided, then your RC is a ring. And here the important thing once again is there is one ring. There is no 2, 3, 4. There was only one ring. So here are some examples. So you are right-sided and you're outside, but you might not include infinity. And you are left-sided and your RC is inside, but you might not include 0. And if two-sided, then you are likely a ring. Okay. And finally, then we have some property about it being rational. Then rationals, then ULC is bounded by poles over infinity. And if you are rational and right-sided, then you are, as we said, right-sided, you should extend the outside. So, but now it's rational and it's bounded by poles, so it should be outside of almost pole. And then we have this HR thing. So we say if rational and if it's rational, then if and only if you are causal, that you will include the equal infinity. Rational and right-sided. And similarly, rational and left-sided, then you should pick the leftmost OC. So you are inside the innermost non-zero pole. And also whether you include 0 is dependent on whether you are anti-causal. Okay. Those 0 and infinity analysis, once again you can just look at this Laplace transform Z transform definition and think about and look at then as a power series of Z and think about whether this series diverge at 0 or infinity. Okay, and 15 minutes should be fine. Okay, then we have inversely transform. And here we have 3 methods. So the first 2 methods are like the method in Laplace transform, and but we have a third one that's unique to Z transform, this power series. And the first one is the counter integral. And once again, this is most general, but we don't know how to do here. We have a counter integral inside LC, which will be a circle because our LC look like a ring. And so we'll have a counterclockwise circle inside your LC, and you need to do this integral to know your inverse the transform. And method 2 is the partial fraction expansion. But as we said, this is more tricky now because you want to break basically into this form. It's something over 1 minus AI z minus 1, because that's what our example 10.1 and 10.2 give. And to do that, basically you want to do partial fraction expansion, but you want to express in terms of polynomial of z minus 1, because you have z minus 1. So you won't get into factors of z minus 1. Okay? So hopefully you can do that. And so here with the example that you will successfully break into those 1 over 1 minus 1 over 4z minus 1, and another term with 1 minus something over 1 minus 1 over 3z minus 1. And so you see this term has a pole 1 over 4, and this has a pole 1 over 3, etc. Then you will look at the LC and decide that whether you want to use 10.1 to get back into this right-sided exponential, or you want to use 10.2 to get this left-sided exponential. Yeah. And okay. So there's a question of how do you do with higher order term that we don't say for now. Let's look at method 3 first. So method 3 is that you just look at this expression, this definition of Z transform, and then find out that it's a power series expansion. And basically you say that if your x over z look like a power series of z, then you can just read x over n as a coefficient to the coefficient x over n as a coefficient to z to the minus n. Basically, you just compare this to your expression of x over z, and you can read x over them from them. But usually your x over z is not in this form already, then you can do something to try to make it look like this, and it's either long division or Taylor series expansion. And detailed calculation you can look at the lecture notes. Okay. And finally we have the properties. Okay, we're short on time, so let's don't go through the property. I guess we can look at the particular interesting one. So particularly interesting one is circle length. So I think this is very different to the Laplace transform. So when you now scale in z direction, so it's scale in the I draw is very ugly. Okay, maybe this. Okay, so this thing scale in z domain. So this corresponds to shifting in the S domain. So when we have a shifting S domain, like S go to S minus S0, then it's rather easy e to the, you get HR e to the S. I think you get e to the ST on the time domain. But now that you have the shifting Z domain, things will get a bit more interesting here. Yeah. Okay. Yeah. You have the scaling in Z domain, and yeah, I think this is a more general form, most general form. So you want to divide your Z by Z0, and you will get Z0 to N in your time domain, etc. And your RC will get scaled in a funny way. You basically multiply your RC with Z0. Okay, and that's that. And how do I? Yeah, and we have, once again, we have an initial value theorem, but we don't quite have final value theorem here. Want to say is okay, and then we have this table for Z transform, and so here once again we have our favorite 5 and 6 here. That's the example 10.1 and 10.2 that can let you do the partial fraction expansion and the inversely transform. And what's important here are kind of the thing not here. So like the Laplace transform, you can do a differentiation on the. Oh, so maybe I should mark that. So wait, yeah. So differentiation here will also return in a funny way. So differentiation here, you see that you take a differentiation of z on here, so the big X dz, but because the difference was a little bit weird, you also want the times the minus z times the HRZ here, and then you got a sin nx here. Okay. So differentiation formula is funny because you have HR multiplication of z here, and RC HA doesn't change. But anyway, the funny differentiation formula give you this funny result on this higher power of 1 minus alpha z minus 1. So you see you have a square here, but the upper side you also need alpha z minus 1 here. And yeah, and then we don't have higher order expression here. So yeah, so if you have multiple roots of z minus 1 in your rational function, then we don't quite know how to do. But if it's only second order, then you can try to fit it into this form. Okay. So the partial fraction expansion inversion of the transform is be harder than the Laplace transform because we don't have the nice formula in terms of the partial fractions. You see the higher order partial fraction has this funny form. Okay. And yeah, you should try to fix this form if you get second order. And I think if you are third order, then maybe you can try to derive them from the differentiation here. Well, my or might not be in a final, but if it's in a final, then it's a harder problem. Okay. Anyway, so let's look at the last part. So we have 5 minutes. So this part, we want to say a little more about analyzing property of system using the Z transform. So once again, system function look like this. So big Y of Z equal to big H of Z times big X of Z, then this big H of Z is your system function. And from big H of Z, you can decide whether your system is causal stable. And causal here, we actually got if only if condition that's different from the Laplace transform. Laplace transform, we only have one side. So we have the if. But anyway, so here is causal if only if ours is exterior. So it's similar to the right side. But now we have this HR condition. So we can say that if you also include infinity, then this is a if only if condition. Okay? So your system is causal if only if your RC is almost one and almost one and also include infinity. And for rational system, you can translate those two. So exterior one basically same as is outside or rightmost pole. So basically the same. But include infinity, you can rational function, you can see whether you converge infinity easily. You just need because the rational function is the numerator divided by the denominator, so you just want the numerator degree less or equal to the denominator degree, so the numerator don't grow faster than denominator. Yeah. So causality is an easy way to totally characterize. And then stability is basically the same. So stability in Laplace transform, you want to include the geometric axis, and in a Z transform, you want to include a unit circle. Okay. And finally, you want to say how to solve the linear constant coefficient differential equation. And just as usual, you apply the Z transform everything. And then you find out that this time shift here, so this minus something, say minus 1 it give you a extra z minus 1, and minus 2 will give you a z minus 2 etc. Then yeah, so you find out that your big Y divided by big X is a polynomial in z minus 1, which can be turned into a polynomial in z. But maybe the polynomial in z minus 1 form is more useful because depending on the quadrant asked, but say you want to do inverse Z transform to get back to small h, then you want to do partial fraction expansion on this. And that'll be easier when you have z minus 1 term. And anyway, but just like in Laplace transform, this is incomplete because this only tells you the algebraic part of the z transform. You also need other condition to find the RC. For example, maybe you are initial rates, then you know you are causal and you need to pick the rightmost RC, etc. And finally, this is the general expression for solving a difference equation. So yeah, so you have the sum A and times Y and the sum B times X. Then your H is sum B times Z to the minus K and the sum A, aka Z to the minus K. Okay. And yeah, so I think that's it. There can be questions. There will probably be questions about the test you on how will you know all the properties and piecing them together to derive the property of the system, etc. Okay, I think we have 2 more minutes. That's about right time. So any question? Otherwise, I think we can stop here. And yeah, good luck on the final on Friday. Okay, yeah, let's stop. Okay.